I'm Yaniv.
Hello, I'm Blake.
Hi, I'm Lucian.
Hi, and I'm Gordon.
And this is the TrainMaster 6000 program that will help station managers sort of figure out what the min cut value in their network is. And so here are the contents. So today we're going to be talking about why trains. We're going to ask our original question. We're going to show you our implementation. We're going to talk about problems that we've had along the way. We're going to talk about the max flow min cut problem, which is our way of solving it. And then we're going to talk about the results, and we're going to conclude with what we took away from this project. So, why trains? Well, all of us in this project basically take the train pretty much daily. For example, for me, I have to commute from Newton, which is where I live, to Northeastern pretty much every time that I want to get on campus. So, trains are something that for me are part of just day-to-day life. And we were all kind of interested in getting to know how the Ford-Fulkerson algorithm applies to train networks so that we can solve problems like helping us find sort of like where the bottleneck in our day is going to be or something like that. And we figured that this was going to be simple enough so that we can have like enough time to achieve it in the time frame that we were given. And so I'm going to pass it off to Gordon, who is going to talk about our question.
Hey, yeah, so looking at our original question, we basically were taking a look at how can we get groups of passengers from source station to a destination station as efficiently as possible. Of course, this is like a really general question, so we've simplified it a little bit. We're taking a look at just trains and their capacities. We're not looking into like train delays or like times of day or stuff like that. We're basically taking a simplified question and looking at how can we get this group of people across an imaginary country as efficiently as possible without any of the outside factors, just looking strictly at trains and their capacities. And then on the next slide, we've start talking about how we've implemented this. So we've generated a Python program which has a few components to it, but the first is we try to generate a graph, and by doing so, we've allowed for either a manual implementation where we set up a command line program that allows users to enter in their source and their destination nodes into the graph by hand and their edge weights. And then we've also done so you can upload a file and just do it quicker like that. So if you have a graph that you want to check multiple source and destination nodes or something, you can just implement one file and then repeatedly use it. So then once we've got the graph generated, this will go ahead and like generate a full graph. So all the nodes, all the edges are stored in a graph class. And once that is set up, we can then run the Ford-Fulkerson algorithm on the graph to find the max flow. And the Ford-Fulkerson algorithm was built using BFS as its search algorithm. So as it goes through each iteration and builds its residual graph, it will use BFS to check to make sure it can still reach from source to destination. If it can't, then we know that we found the max flow. And if not, then we know we can still push more throughput through the graph to the destination. And once this is done, we're able to see the max flow and determine, I guess, how many passengers we can push through the train system at once for any particular graph. And yeah, I will pass it off now to Lucian to talk more about specific examples of these graphs.
Hello. On this graph that I created for testing purposes, this graph has an obvious bottleneck. You can see it on the edges that lead into node 9. They all have edge weight of 1, so the max flow in this case is 3, and that was easily checked, and the algorithm came up with the correct max flow. Next slide. This is a more complicated graph that represents a train system through an imaginary country, but we solved this by hand and then checked it with the algorithm to make sure the algorithm is working, and we got a max flow of 210. Now I'll pass it on to Blake, who's going to talk how we applied this to the Boston MBTA.
Thank you, Lucian. So the graph might be just a bit hard to see as it was created in Visio and now on our PowerPoint slides. So please bear with me. This is actually the Boston MBTA found on their website. We took the graph and had to do a little bit of parsing the data to try to figure out what is our paths, basically. So we also had to do a bit of pruning as well to narrow down a bit more of our data that we were looking for and that we also might be finding useful. So this is a pretty complex graph, but it is color coordinated and the lines are color coordinated. A full of the graph can be provided as well. And as you can see here, we do have them as different colors to show the different lines that are currently running in Boston. They may not be the separate lines that you might see on the MBTA, but they are kept orderly and separate for our purposes for testing. So this is our test graph, and we'll be showing our max flow on our results slide in the near coming future. So please go to the next slide. So there is one key weakness in the data that we were using. We have the data for number of passengers found between stops. And that is useful, but it's not useful completely with answering all of our questions that we have with our project. We need more data to answer our questions, and this occurs in some projects. If we could have maybe more different kinds of variables entered or even automatically generated, maybe the time between stops, how long it took, we might be able to get an idea about what our throughputs actually are and really more accurately where the bottlenecks lie for the maximum flows getting through our train systems, especially our Boston MBTAs that we probably all take every day. So that is a bit of a limitation in finding useful data for measuring all of our edges for optimization. So,
so
if you take it over.
yeah, so basically to kind of alleviate some of those issues when we were implementing this, our solution was to simplify the problem. So rather than asking our original question, we asked a modified question, which is, what is the min cut value itself of the system, so that the train station manager can know essentially what the bottlenecks of the system are. And so because we know that the max flow of the system is equivalent in value to the min cut value, the train station manager can then use the max flow of the system from a node to another node to get the value of the minimum cut between those two nodes to kind of know where their bottlenecks lie and like what the throughput of that path is. And so the result for the graph that Blake used, we were trying to see kind of how to get across Boston from Boston College to Wonderland. And from the graph, it's kind of hard to see, but that is the rightmost red node to the all the way at the bottom to the rightmost purple node all the way at the top. And essentially, the min cut value on that system is 10, and you can see that because between BU East and Blandford Street, there is a value of 10, and there's no way to kind of avoid that in the path between Boston College and Wonderland, and so that's kind of like the bottleneck of our system. And so that indeed is the smallest value edge, and so in the path from Boston College to Wonderland, and so we know that we have actually found the correct max flow from the Boston MBTA system here. And so just in conclusion, for me at least, I will probably be using this kind of system for unsupervised machine learning, specifically for data mining, because network flows are used in that application. And as well, I work at a robotics company that works on Internet of Things growable machines. And so what we kind of look at is nutrient flow. And so because we have 4 different pipes of nutrients and kind of different amounts of data, we can actually set that up as a network flow problem. So that actually might be an application in the future for me. For Lucien, we have a different problem.
I thought this was a classic algorithm, is useful for future interviews and also solving LeetCode problems. And it's also a great problem for solving other kinds of problems that are reductions of forward focusing. Blake?
Yeah, I thought this was a great idea and use case for throughput problems as well. Maybe train systems or maybe scheduling issues maybe that might come in the future, especially during a leak code interview. It's an interesting way to see how public transport can also maybe be a bottleneck and help alleviate possibly to find where those bottlenecks are at any given moment. Thank you. Gordon?
Yeah, and just to wrap it up, I guess over the course of this project and really the whole course, it's been kind of cool to implement one of the algorithms we've learned into a real everyday situation where you might not think, like while you're waiting at the T, that wow, I could use Ford Fulkerson to like simplify this problem or something. So it's great to use something from class in like everyday life and see how we can use algorithms to simplify everyday life and make things easier for everyone. So yeah, that is our conclusion to our project, and hopefully we've drawn some good conclusions here.
Thank you for hearing our presentation. We hope you all have a wonderful day.